Welcome. This is Ralston Valley High School Chemistry's AP Chemistry Lecture Series, in which we're going to examine Chapter 13, Lecture Number 2. We will discuss the reaction quotient Q and ice tables. Let's get started. So in our previous conversations, we've talked about how chemical reactions involving equilibrium systems tend to react until they reach their point of equilibrium. And generally, when we've dealt with these equilibrium systems, we've given you initially some initial amount of reactants present in the system, and then watched as those reactants were consumed, in doing so forming products. But because the systems we're examining in equilibrium systems are reversible processes, we wouldn't necessarily have to start off just with reactants present in our system. It would be possible to imagine a system in which you start off both with reactants and products present. And in such a system where there are both reactants and products initially present, we would need some quantitative tool that would allow us to tell us the direction the system would move in order to establish its point of dynamic equilibrium. Now, for some systems, this is very, very easy to understand. If you imagine a chemical system in which you have reactants on one side and products on the other, if you only start with reactants present in the system, the direction the system could shift to get to equilibrium would be towards the products. Or conversely, if you started with a system where you only had products present, in order to get to the equilibrium point, the system must therefore shift to the left, producing more of the reactants. But when there are both reactants and products present in our initial system, it's very difficult to qualitatively determine the direction the system must shift to get to its equilibrium point. And that's where today's calculation comes in. We're going to be calculating today a value we call the reaction quotient Q. Now, the reaction quotient Q is the exact same calculation as the equilibrium constant KEQ. That is to say, both the reaction quotient Q and the equilibrium constant KEQ are defined as the ratios of the concentration of the products over the reactants. Again, always raised to the exponent powers of the coefficients from the balanced chemical equations. The distinction between these two calculations is that whereas the equilibrium constant KEQ is calculated using equilibrium concentrations of those species, the reaction quotient Q is calculated using the initial concentrations of those species. So let's consider for a moment here, folks, about how that's going to look and how we can use that calculation of the reaction quotient Q to determine the direction the system will shift in order to establish equilibrium. Again, I'm going to write out here, because both Q and KEQ are the ratios of concentrations of products over reactants. If I imagine for a moment here that I calculate a value of the reaction quotient Q, and I find the value of reaction quotient Q to be greater than the value of the equilibrium constant KEQ, that would tell me then that the current ratio of the concentrations of the products over the reactants is larger than that ratio would be if the system were in equilibrium. And therefore, to get to that equilibrium point, the value of Q would have to get smaller. To make the value of Q smaller, the concentrations of my products, that is the things in my numerator, would have to decrease, and the concentrations of my reactants, that is the things in the denominator, would have to increase. Which implies, therefore, this system would have to shift towards the reactants in order to get to the equilibrium point of the system. So we would say, therefore, if Q is larger than K, the system would therefore shift to the left towards the reactants to establish equilibrium. Now, conversely, if I again made a calculation of the reaction quotient Q and compared it again to KEQ, if the value of Q was smaller than KEQ, that would tell me that my current ratio of products over reactants would be smaller than that ratio would have to be for the system to be in equilibrium. And therefore, again, to get to the equilibrium position, the value of Q would have to get larger. Implying, therefore, my numerator would have to increase and the denominator would have to decrease. If the numerator increases, that implies that my concentrations of the products would have to go up, and the concentration of those reactants in the denominator would have to go down, corresponding, therefore, to a shift in equilibrium of this system to the right towards the products. So in the event that Q is less than KEQ, this system would therefore shift in equilibrium towards the right in order to establish equilibrium. What would happen if the system had a current set of conditions that yielded a Q value which was equal to the value of the equilibrium constant KEQ? By the same logic we've applied, that would currently tell me then that the current ratio of products over reactants would be equivalent to what that ratio would be if the system were in equilibrium, and therefore, by definition, that system must be in equilibrium. So if Q is equal to KEQ, we would not expect to see any shift, either left or right, as the system is currently in equilibrium. And that's really all the reaction quotient Q does for us. It's used to predict the direction of shift the system must experience in order to establish equilibrium. So let's use this idea now on our next couple of slides in order to make some quantitative calculations involving equilibrium systems. Let's move on. All right, for our next slide here, we're going to have a look at an example problem relating to the calculation of the reaction quotient Q for a chemical system in dynamic equilibrium. If you have a look at the equation we've given you here, this is an equation describing the decomposition of limestone, which is calcium carbonate, CaCO3, in the solid phase, forming, as products of that decomposition reaction, calcium oxide, a solid phase species as well, and the gas phase species carbon dioxide. And the question is going to give us the following information. At a temperature of 900 degrees Celsius, the value of the equilibrium constant, Kp, for this reaction is 1.04. Now, in order to produce this system at equilibrium, at a low temperature, we take solid phase carbon dioxide, that is dry ice, and mix it together with calcium oxide and calcium carbonate into a reaction chamber with a volume of 50 liters. The temperature of the system is then raised to 900 degrees Celsius, causing the dry ice to sublime into gas phase carbon dioxide. Now, with this setup for our system, the question is going to ask us here, for the following reaction mixtures, will the initial amount of calcium oxide increase, decrease, or stay the same as the system moves towards its equilibrium point at the temperature of 900 degrees Celsius? So as a starting point here, let's recognize because we're dealing with equilibrium systems, the very first thing we should do is to write the equilibrium constant expression, KEQ, describing this chemical system. And as always, the equilibrium constant KEQ is the ratio of the concentrations of the products over the reactants. Now, importantly here, folks, note that this is a heterogeneous equilibria in which two of our species, that is the calcium carbonate and the calcium oxide, are solid phase species. And as we've discussed in our previous lecture, because solid phase species do not change in concentration depending upon the amount of the solid present, those solid phase species therefore do not impact reaction rates and as such don't affect the equilibrium position of the system. Which means therefore this is a very easy KEQ expression to write. The equilibrium constant for this system, that is going to be Kp, because we're defining this in terms of pressures, is going to be only dependent upon the partial pressure of carbon dioxide gas. So here my Kp is equal to partial pressure of CO2. Now that we've got the K expression defined, let's have a look at our reaction mixtures. The first thing I want you to notice here, folks, is in the first reaction mixture here, I've got apparently 655 grams of calcium carbonate and 95 grams of calcium oxide. But as per our previous conversation, neither of those two species is going to affect the equilibrium position of the system because they are solid phase species. All that really matters in this is the partial pressure of the CO2 gas. So if I have a look at the partial pressure of CO2 in the first system, I was given here a partial pressure of 2.55 atmospheres. And using then my expression for KEQ, I can now define a value for the reaction quotient Q for this system. Because Q is calculated using the same calculation as KEQ, using the initial pressures rather than the equilibrium pressures, that would imply therefore that Q in this system would be 2.55. And recall again, the entire purpose of Q is to compare to the value of KEQ. 2.55, my current value of the partial pressure of CO2, is greater than the value of Kp given to me for the system of 1.04. Implying, therefore, the current partial pressure of CO2 is greater than that partial pressure of CO2 would be at equilibrium. And as such, to establish equilibrium, our system must therefore shift towards the reactants, that is, shift to the left. Now again, once we've established a shift to the left must occur here, recall the question was asking us, what would happen to the amount of CaO present? Now again, importantly, the concentration of CaO would not change because solids do not change in concentration as you add more or less of them to the system. That being said, however, as the reaction shifts to the left, calcium oxide is consumed as calcium carbonate is formed. Therefore, the left shift expected in the system would cause the amount of calcium oxide in the system to decrease. Now, the next two reaction mixtures have different amounts of calcium carbonate and calcium oxide present. That is 780 grams of calcium carbonate and 1 gram of calcium oxide respectively for the first reaction, and 0.14 grams of calcium carbonate and 5,000 grams of calcium oxide for the second reaction. That being said, again, recall the amounts of the solid phase species don't impact the equilibrium position. All that matters in these two is to recognize that the partial pressure of CO2 gas in the system is equivalent for both of these reaction mixtures at 1.04 atmospheres. And again, if I were to calculate the value of the reaction quotient Q, which again is equivalent to, in this case, the partial pressure of CO2 gas, that would imply, therefore, that for both of these systems, the partial pressure of CO2 of 1.04 atmospheres is equivalent to the value expected from the Kp for this expression of 1.04. That being said, that implies that Q is equal to KEQ for both of these reaction mixtures, and therefore both of these systems are currently in dynamic equilibrium, and we would therefore expect no change to the amount of calcium oxide present in our system, in either the mixtures 2 or 3. Last but not least, have a look at mixture 4. In this time, we give you 715 grams of calcium carbonate, 813 grams of calcium oxide, and a partial pressure of CO2 gas of 0.211 atmospheres. Now, again, looking at the value of my reaction quotient Q, which in this system would be equal to simply the partial pressure of CO2, which would be 0.211 atmospheres. Now my value of Q is less than the defined value of Kp of 1.04. Implying, therefore, my current ratio of products over reactants is smaller than that ratio would be at equilibrium, and therefore to get to equilibrium, this system would have to shift towards the products to produce more CO2 gas. As we shift towards products, the calcium carbonate is consumed and calcium oxide is produced, implying, therefore, as this mixture would expect a shift to the right, we will therefore see an increasing amount of calcium oxide in our system. So again, a real quick and easy example of how the reaction quotient Q can be used to determine the direction of shift to established equilibrium. Let's move on to our next slide. On our previous slides, we looked at how we could use a calculation of the reacting quotient Q to determine a direction of shift as the system establishes its point of equilibrium. Now that we have this framework, we're going to go ahead and move on to something which all of you have been exposed to in our first year chemistry class, which is the mathematical framework by which we're going to examine equilibrium systems, which we refer to as ice tables. An ice table is simply an organizational tool that's going to allow us to make calculations as to how the concentrations of species change in a chemical system as equilibrium is established. The ice table stands for, it's an acronym here, standing for I for initial, C for change in concentration, and E for equilibrium concentrations of our species. Now, again, as a quick note before we jump into an ice table here, remember that these ice tables are essentially tracking changes in concentrations of species, which for aqueous solutions are almost always going to be expressed as molarities. For gas phase species, we might choose to express that concentration either as a molarity or alternatively as a unit of the partial pressure, recognizing again that the partial pressure of a gas is directly proportional to its molarity within a system. Importantly, the values in the ice tables cannot be expressed in units of moles, because again, equilibrium points are established based upon changes in concentration, not changes in the number of particles directly. So, with this as a framework, let's go ahead and have a look at a generic ice table here. You'll see I've got a generic reaction in which gas phase species A and B are reacting together to form the product C. And I've got on my first column of the ice table here, those three letters there, ICE, which again stand for initial, change, and equilibrium concentrations. Along the first row of the ice table column, you'll see I'm going to line it up so that it lines up directly below the species within the balanced chemical equation. I've got here measured the concentration of species A, the concentration of species B, and the concentration of species C. Into this ice table, we're going to take the given pieces of information, whether those are initial or equilibrium concentrations of the species, and use this to determine how the other concentrations of the species must change as the system approaches equilibrium, making use of the stoichiometric coefficients from the balanced chemical equation to allow me to understand how the proportional changes in concentrations are going to affect one another as the system establishes its equilibrium. So with this generic framework, let's take a look and see how these problems will work on our next couple of slides, starting off with what we refer to as an easy ice table on the next page. So for our first example ice table we're going to work through here, I want you to start by recognizing the type of problem that we're going to give you here is what we call an easy ice table. And please note that even though we're going to call this an easy ice table, the real difficulty in solving these things is the actual identification that that's what you're dealing with in the first place here. So just because it happens to be easier in terms of the math doesn't mean it's necessarily easier in terms of recognizing how to solve the problem. So let's go ahead and start off here to recognize that an easy ice table will be identified as such because in addition to giving you initial concentrations of some of the species present, we must also give you a concentration of at least one species at equilibrium as well. Generally, the purpose of these easy ice table problems is to allow us to calculate a value of the equilibrium constant, either defined in terms of partial pressures, that is Kp, or in terms of concentrations, that is Kc. So with this goal in mind, let's have a look at example 2. Example 2 tells us here at a particular temperature, a 2-liter flask initially contains 0.300 moles of phosphorus trichloride, PCl3, and 8.5 times 10 to the negative third moles of phosphorus pentachloride, PCl5. And one additional piece of information, we're also going to tell you here at equilibrium, there is 2.00 times 10 to the negative third moles of chlorine gas present in the reaction flask. And with this given information, we're going to be asked here to calculate the value of the equilibrium constant Kc. Now, as a starting point here, folks, we've got a reaction written for you here for the balanced chemical equation describing the decomposition of phosphorus pentachloride, PCl5, breaking down to form phosphorus trichloride gas and chlorine. And down below, I've given you the setup for the framework of an ice table. Along the first row, we're going to put the concentrations of the species which correlate to the balanced chemical equation above. That is, we've got the concentration of the phosphorus pentachloride, PCl5, the concentration of PCl3, and the concentration of Cl2. And then again, along the first column, we're labeling here our 3 different positions of the system: the initial concentrations, the change in concentrations, and the equilibrium concentrations for our system. So we've got the ice table set up. Let's now go ahead and take the given information and see where it fits within our table. Now, important to note here, folks, within the ice table itself, we are always going to be measuring in either concentrations or partial pressures, not in moles. And in this problem, I gave you moles of the reactant species present. So the very first step is we need to find the concentrations of the PCl3 and the PCl5 under our initial conditions. Again, by definition, a concentration is a molarity, that is, the moles per liter. So for our PCl3, we have our 0.300 moles of that species divided by the 2.00 liter volume of a reaction flask, yielding to a molarity of 0.150 molar. And then similarly for the phosphorus pentachloride, PCl5, we've got our given 8.50 times 10 to the negative third moles divided by the 2.00 liter volume of reaction flask, yielding a molarity of 4.25 times 10 to the negative third molar. So I now know the initial molarities of those 2 species, and I'm going to place them then into my ice table in the appropriate locations. So again, on the row for initial concentrations, and then in the columns corresponding to the different concentrations of these species, we'll put those 2 values of 4.25 times 10 to the negative third molar for the PCl5 and 0.150 molar for our PCl3. Now, given that I did not tell you anything about the initial concentration of the other species present in the system, that is the chlorine gas, you're welcome to assume, if you have not been told additional information, that the values of these concentrations will be zeros. So I'll throw a 0 in there for the initial concentration of Cl2. Now, there's one additional piece of information which was provided to us here, and that was that there is an equilibrium concentration of chlorine gas, which was given by taking our 2.00 times 10 to the negative third moles of chlorine and dividing it by the 2.00 liters of our flask, yielding an equilibrium concentration of 1.00 times 10 to the negative third molar. And importantly, I'm going to take that equilibrium concentration and put it now in the third row of our ice table, that is the equilibrium row, under the species chlorine Cl2. All right, so we've now accounted for all of the given information. Now, before we move forward here, folks, let's have a quick conversation relating to the value of the reaction quotient Q for this system. If I define the value of my equilibrium constant, as always, it is the concentration of the products over the reactants. For this system, that would give me a K value of the concentration of PCl3 times the concentration of Cl2 divided by the concentration of PCl5. And if I wanted to now calculate a value of the reaction quotient Q for this system, I could now plug in my initial concentrations of each of these species to determine that value of Q. So again, products over reactants would give me, for PCl3, the concentration of 0.150, times for chlorine is 0 there, and then divided by the PCl5 concentration of 4.25 times 10 to the third. Clearly, this Q value is going to turn out to be 0. And this tells me something I probably already knew. Given that Q is 0, by definition, it must therefore be smaller than any given value of KEQ that could exist, and therefore, to establish equilibrium, this system must shift to the right towards the products. And a shift towards the products now will mean that I'm going to end up increasing the concentrations of PCl3 and Cl2, while I decrease the concentration of the reactant species PCl5. Here now is where I'm going to talk about that changing concentration. Because I know PCl5's concentration is going to be decreasing, but I don't know by how much, I'm going to label it here now in my ICE table here as a change in concentration of minus some amount x moles per liter as this system approaches equilibrium. And now that I've defined one of the changing concentrations, I can now also define the other changing concentrations as well of the other species present. Looking at the mole ratios here, I see that PCl5 decomposes in a 1-to-1 ratio to form both PCl3 and Cl2. Implying, therefore, if I recognize that PCl5 is going down in concentration by x moles per liter, then my product species, PCl3 and Cl2, must therefore be going up in concentration by the same proportional amount, again due to that 1-to-1 mole ratios. So whereas PCl5 goes down by minus x moles per liter, PCl3 and Cl2 would both be correspondingly going up by the same x moles per liter. So I'll label those as plus x's for both of their changes in concentration. And at this point now, I want you to recognize why we call this an easy ICE table. Have a look at the species Cl2. We currently know everything about that species, including the initial concentration, its change in concentration defined in terms of x, and its equilibrium concentration. And therefore, I must know that the initial concentration of 0 molar plus the change of x moles per liter would yield for us here the equilibrium concentration of 1.00 times 10 to the negative 3 molar. Therefore, x must itself be equal to that value of 1.00 times 10 to the negative third. Now that I have found x, finding the other equilibrium concentrations of the species is trivial. Because for PCl3, I started off at 0.150 molar and it went up by x moles per liter. At equilibrium, therefore, I would add the 0.001 mole per liter there of the change in concentration to the initial concentration of 0.150, yielding an equilibrium concentration of 0.151 molar. And likewise for my reactant species, PCl5, that started off at 4.25 times 10 to the negative third molar. It went down by x moles per liter, and when x is in this system 1 times 10 to the negative third molar, that would now leave me at an equilibrium concentration of 3.25 times 10 to the negative third molar. And I therefore now have solved the ICE table. I know all of the equilibrium concentrations of all of my species. From here, it's very easy to calculate the value of the equilibrium constant KEQ. Again, KEQ we defined as the concentration of the products over the reactants. That was the concentration of PCl3 of 0.151 molar times the concentration of Cl2 of 1.00 times 10 to the negative third, all divided by the concentration of our reactant PCl5 of 3.25 times 10 to the negative third. Now, importantly here, folks, because K is literally just a ratio of concentrations, the actual units on this ratio would be changing depending upon the relative numbers of moles of products and reactants that are formed, and as such, the units on a K value are not really meaningful or important. So we're just going to go ahead and assume K is essentially a unitless value as a ratio. When I calculate this value using my calculator, I get a value of 0.0465 for our K value, implying here we've got a system with a small k, which would therefore favor the reactants side of our system when this system establishes its point of equilibrium. All right, so easy ICE table taken care of. Just use the framework of that ICE table to determine the value of your change in concentration x, and then from there you can correspondingly determine the other concentrations of the species at equilibrium and use it to determine a value of the equilibrium constant KEQ. Now that we've seen an easy ICE table, on our next pages, we'll have a look at harder ICE problems, and we'll give you some tips for solving these problems when you're not given an equilibrium concentration of any species. All right, so on our next couple of slides, we're going to be having a look at less easy ICE tables. You probably remember spending lots of time with these during your first year chemistry class because these are the ones that tend to both be most commonly encountered, but also the ones that tend to be significantly more difficult in the approach to solving the ICE table. A less easy ICE table can be recognized if there is no equilibrium concentration of any given species. And as such, the framework we gave you on our previous slide for solving the easy ice table won't work. So if we find ourselves in a position where we do not have an equilibrium concentration of any species given, we're going to go ahead and follow the following sequence of steps to get to the equilibrium concentrations in solving the ice table. First and foremost, number one, we've got to make sure you're working with a balanced chemical equation, because the mole ratios of that balanced chemical equation will determine the relative changes in concentration of each of the species as the system approaches equilibrium. Step two is to make sure you understand the direction the system must shift in order to establish equilibrium. This could be easy if there's zero concentration of either a reactant or a product present, because with a zero concentration, you know the system must shift in such a way that that concentration would go up. But if it's not so straightforward and you don't have any zeros under your initial concentrations, in that case, you're going to have to calculate a value of the reaction quotient Q to determine the direction the system will shift to establish equilibrium. Once you have done so, your next step is to set up your ice table, plug in any given information you've got about the initial concentrations of any species present, and then define the change in concentration in terms of X, paying attention again to the relative coefficients from the balanced chemical equation to determine the relative changes in concentration of each species. At this point, we're then going to solve for X. Now, this is not going to be quite as straightforward as it was in the previous problem. In these examples, generally the process we'll follow is going to be following what we call a small k assumption method. The small k assumption method is going to be based upon the idea that for a system where the value of k is very, very small, the changes in concentration are also likely to be very, very small as the reactants react to form products, because a small k would imply a small ratio of products over reactants. If you find yourself in a position where you're not able to make such an assumption to simplify your math, as we'll see on the next example, you might have to then take into account other more difficult mathematical relationships, such as maybe a quadratic formula or other means solving graphically or using a solve function on your calculators to solve the ice table for X. Once you have determined the change in concentration X, your then next step would be to determine the equilibrium concentrations of all species. If you happen to use any mathematical assumptions to simplify your work along the way, you need to check and prove that those assumptions are valid by not introducing undue error into your calculations, generally an error greater than 5%. Now, hopefully all of these steps look at least somewhat familiar to you from last year, but if not, that's okay, because we're going to definitely do some example problems over our next unit here that will help to reintroduce this idea. So let's move on to look at a hard ice table example problem on our next slide. All right, we're moving on now to our hard ice table example. For example number 3 here, we're going to give you the following information. If 2.0 moles of carbon dioxide gas is initially placed into a 5.0 liter reaction vessel, we're going to ask you to calculate the equilibrium concentrations of all species given a value of the equilibrium constant Kc of 2.0 times 10 to the negative 6th at this particular reaction temperature. And we're providing you now with the equation below, which describes carbon dioxide gas, that is CO2, breaking down into carbon monoxide gas, CO, and O2. So we've got our balanced equation there for you at the top of our ice table. Let's go ahead and follow our framework we've provided you on the previous slide to determine the equilibrium concentrations of all species. Starting off by initially calculating the concentration of the molarity of the CO2 gas in our reaction flask under those initial conditions. So if I have a 2.0 mole sample of CO2 in a 5.0 liter flask, this yields for me here a measured molarity of 2.0 divided by 5.0, which would yield 0.40 molar. I'm going to place that initial concentration of 0.40 molar into the column under the CO2 gas in my ice table for that particular initial concentration. Now, note here, folks, that was the only species we told you that was initially present in the flask, and therefore I'm welcome to assume initial concentrations of both of those products of 0 molar. So now that I've got those initial concentrations here, note that this is not as simple as the previous ice table that we solved, in that I've not provided you with any equilibrium concentrations of any species. But even though we do not know the equilibrium concentrations of any species, that does not necessarily mean that we're stuck. We can still define the changes in concentration for our current system. Recognizing here that I've got 0 product present in this system initially, I must therefore see an equilibrium shift to the right, as my Q value again here will be 0, less than any defined value of Kc. And as this system shifts right, we would therefore be producing products and consuming reactants. So I'm going to define my change in concentration now as, for the species CO2, a change in concentration of minus 2x moles per liter. Again, recognizing that I need to be paying attention to the coefficients from the balanced equation here to determine the relative changes in concentration of each of these species. So if CO2 is going down in concentration by 2x moles per liter, the species carbon monoxide on the product side must be therefore correspondingly going up by the same proportional amount of plus 2x moles per liter, and then the oxygen would be increasing in concentration at a amount of plus x moles per liter, again, since 2 CO2 decomposed to make only one oxygen molecule in this system. So we've now defined our changes in concentration, recognizing again that the coefficients from the balanced equation will inform the changes respectively for each species. And now I can define my equilibrium concentrations in terms of x in this system. Whereas the CO2 started off with an initial concentration of 0.40 molar and went down by a change in concentration of minus 2x moles per liter, at equilibrium, we must find ourselves there with 0.40 minus 2x moles per liter of the CO2. And then for CO and O2, these are easy. Both of these started at 0 moles per liter. CO2 went up by 2x moles per liter, so at equilibrium, we would therefore be at 2x. And by that same logic, oxygen would now be at x moles per liter. So we've now essentially filled out all of the information in our ice table we possibly can. In next step will be, let's go ahead and have a look at our value of the equilibrium constant Kc. Our defined value of Kc was given to us here as 2.0 times 10 to the negative sixth. And as always, that Kc value is defined as the ratio of concentration of the products over the reactants. So if I write out my expression for Kc, it would be equal to the concentration of my product, which would be carbon monoxide, CO, which is going to get squared due to the coefficient from that balanced chemical equation, times the concentration of the oxygen, all divided by the concentration of my reactant, which is the concentration of CO2, which again also will be squared due to its coefficient. And even though I don't have any actual numerical values for those concentrations at equilibrium, I still know what those equilibrium concentrations are defined in terms of x. So I'm now going to go ahead and substitute in to those concentrations the values from my ice table as defined in terms of x for the equilibrium concentrations, which yields for me now an expression of the Kc value of 2.0 times 10 to the negative sixth is now equal to carbon monoxide's equilibrium concentration, which would be 2x, which gets squared, times concentration of oxygen at equilibrium, which is simply from my ice table x, all divided by my reactants concentration of the carbon dioxide, 0.40 minus 2x, which is in its entirety going to be squared in my denominator. Now, at this point, I have an expression, and it looks like an expression I might be able to solve. However, it looks like it's going to be nasty in terms of the math involved, because this looks very much to me like we're going to end up here with a cubic polynomial function, which is nobody's idea of a good time to solve. So I'm going to recognize now that I can simplify this math by having a look at the value of the equilibrium constant Kc. The value of Kc in this system of 2.0 times 10 to the negative sixth is a very, very, very small value of Kc, implying therefore my ratio of products over reactants itself must be a small ratio. And if that ratio of products over reactants must be small, the value of x itself must also be small because my products concentrations in the system at equilibrium are x and 2x respectively. So I'm going to recognize then that a small value of k implies in this system a small value of x. So I'm going to go ahead here and make an assumption. I'm not going to just make the assumption that x is small, but specifically that the quantity 2x is very, very small in comparison to the initial molarity of the carbon dioxide in this system of 0.40 molar. And the reason why I want to make that specific assumption is as follows. If 2x is very, very small compared to 0.40, then my expression we just written there for the equilibrium constant Kc would now become the Kc value of 2.0 times 10 to the negative sixth is equal to, in my numerator, let's simplify here, I'm squaring everything in that parentheses, which means 2 squared is 4, and then x squared times x would give me x cubed. And then in my denominator, here's the tricky thing. If the value of 2x is very, very small compared to 0.40, then 0.40 minus that very, very small value of 2x would essentially be very, very close to 0.40. So I'm going to do a little bit of a mathematical cheat here. I'm going to assume that 0.40 minus 2x is essentially equivalent to 0.40. Now I recognize that mathematically that is not entirely a truth, but it's probably going to be close enough to being true that it's not going to majorly impact the overall calculations that I'm doing here. So I'm going to simplify that denominator now to simply just 0.40 squared. And from this point, this now becomes much, much easier math to solve. To isolate x, I'm going to go ahead and multiply both sides of my equation by 0.40 squared. I'll divide both sides of the equation by 4. Canceling all of that out leaves me now simply with this expression, which needs to now have a cube root of both sides to isolate x. And as I take the cube root of both sides, this yields for me, using my calculator here, a value of x of 0.0043. So I've got a value of x, and yeah, it looks to me like it's pretty small. But pretty small is not qualitatively enough. I need to prove, in fact, that my assumption I made here didn't introduce undue error into my calculations. So in order to do that, we're going to go through a process which we refer to as checking your assumption. In checking the assumption, I'm going to go back again to the specific assumption I made, which was that the value 2x was very small compared to 0.4. I'm going to show just how small that 2x value is compared to 0.40 by expressing it as a percentage. So I'm going to divide my 2x value of 0.0043 times 2 by the initial concentration I assumed it was small in comparison to, which again was 0.40, and then I'm going to multiply that whole expression by 100 to express this as a percentage. And when I make that calculation, I come up with a percentage here of 2.2%, which essentially tells me that the 2x value was 2.2% of the thing I assumed it was small in comparison to, which was 0.40 molar. Now, as it turns out, that's probably for my purposes fine. Because remember, in any sort of calculation I'm doing here, what I'm trying to show is how this would relate to how the actual measured values would be in the lab. And because any given individual measurement that I make in the lab is itself subject to some amount of experimental error, what's important here is just that my calculations aren't any more likely to have error in them than any measurements I would make would be. Because even a well-run lab tends to have errors running around 5% or so. As a scientific community, we generally assume that as long as your assumptions we're making here are not introducing more than 5% error into your system, we're going to accept them as being at least as good as measurements that you would make, and therefore valid for our purposes. So because my 2.2% is less than the 5% range there, I'm going to say, yeah, my assumption here was probably fine. And therefore, now that I know x, I can now determine the equilibrium concentrations of all species. My concentration of oxygen at equilibrium was given to me as x, therefore is equal to the x value of 0.0043 molar. Carbon monoxide's concentration was 2x at equilibrium, therefore 2 times that x value would yield 0.0086 molar. And last but not least, carbon dioxide's concentration at equilibrium was 0.40 minus 2x molar. And then here, watch your sig figs. If I take 0.40 and subtract the 2x value of 0.0086, that leads me to a value of 0.3914. And recall, for significant figures for addition and subtraction, we're going to round to the last measured place value in all of our calculated values, which in this case would be the 100th place. So therefore, this is going to round to 0.39 molar. And this really is then a justification that, in fact, yeah, the x value here really was small because my initial concentration of 0.40 molar hardly changed at all as this system approached equilibrium. That is from 0.40 molar initially to 0.39 molar at equilibrium. All because, again, this x value was small because the k value of this system was itself small, meaning we did not see a large shift to form products as this system approached equilibrium. So we have now followed the hard ice table example. Hopefully this is familiar to you from first year chemistry. Let's now move on to a last couple of slides here for this lecture. Moving along. All right, for our next example problem here, we're going to again work an ice table problem. And as we work this, we're going to notice that there's a significant difference between this ice table and the one we worked on our previous example slide. In particular, in the value of the equilibrium constant Kc is going to be large in this example rather than small as we saw on our previous example. So have a look at example 4, where you're describing a system here in which carbon monoxide is reacting to water vapor to form carbon dioxide and hydrogen gas in an equilibrium state. And we're going to go ahead and set up an ice table again with the ICE along the first-hand column there, and then again the concentrations of each corresponding species involved in the reaction along our top row. And the problem is telling us here, in this instance, we're going to introduce 1.0 mole of each species involved in the reaction below. And we're going to mix them together in a 2-liter container and determine the equilibrium concentrations of all species, given a value of the equilibrium constant of 7.50 at this reaction temperature. So, as a starting point, let's recognize that the values that show up in our ice table, again, must be molarities, not moles, and as such, we need to determine the initial molarities of all species. Again, by definition, molarity is moles per liter, so taking our 1.0 mole of each species and dividing it by our 2.0 liter container, this yields a molarity of each individual species of 0.50 molar, and that includes both the reactant species and the product species, given the information provided to us in this description. So, putting our initial concentrations into the ice table here, let's now go ahead and determine the direction in the system will move to establish equilibrium by making a Q calculation. As always, the value of Q is determined as the ratio of the concentration of the products over the concentrations of the reactants, which in this instance would be the concentration of the product CO2 times the concentration of H2 divided by the concentration of our reactants, carbon monoxide CO, times the concentration of H2O. And this is a very easy calculation to make in this instance because, again, as all of those concentrations of each species are 0.50 molar, the value of Q here clearly now becomes 1 for this system. Now, comparing that value of Q to the given value of the equilibrium constant KEQ yields here for me information that tells me this system has a Q smaller than Kc, implying, therefore, the current ratio of products over reactants is smaller than that ratio will be at equilibrium. Thus, to establish equilibrium, we must shift to the right to produce more product. And as we've determined now, as shift right, I can now define my changes in concentration. For my reactants, these will be consumed as we shift right, so my changes will be, therefore, minus X moles per liter for both carbon monoxide and water vapor. And then we will increase by the same proportional amount of X moles per liter for both the carbon dioxide and the hydrogen gas, as all of these species exist in 1-to-1 mole ratios to one another within our equation. This leaves me now with calculated equilibrium concentrations of 0.50 minus X for both of my reactants and 0.50 plus X for both of our products. So at this point, we now have set up our ice table. Let's now go ahead and use the equilibrium constant expression to help us solve for X. So again, the given value of Kc of 7.50 was equivalent to the ratio of the concentrations of the products over the reactants, which in this case would be the concentration of CO2 times the concentration of H2, which at equilibrium would be 0.50 plus X times 0.50 plus X, divided by the concentration of our reactants, which would be for the CO, 0.50 minus X, and for the H2O, 0.50 minus X as well. Now, at this point here, folks, we might find ourselves thinking that this could be a good time to make an assumption. However, we have to be very, very careful with this. Number one, recall the reason why I was able to make the assumption on the previous slide was because the value of K was small, implying, therefore, the value of X was small in our system. For our current example, the value of Kc here is large, implying, therefore, making an assumption that X is small when I know it, in fact, to be large is probably, mathematically speaking, an unwise assumption to make. Alternatively, number two, if I look at making an assumption here, and I did assume that X was small compared to 0.50, that would simplify my expression down now to essentially 7.50 is equal to 0.5 times 0.5 divided by 0.5 times 0.5, which I know is equal to 1, which is entirely mathematically false. So clearly we are not in a position here where making the assumption makes any logical sense. So instead, we're going to try to take some alternate mathematical pathways to get to a solved value of X. And happily for me, I've got a pretty easy one here. To recognize here that in my numerator, I have 0.50 plus X multiplied by 0.50 plus X, that's really 0.50 plus X squared. The same would be true of my denominator. 0.5 minus X times 0.50 minus X is equal to 0.50 minus X squared. So essentially here now, I then have on my right side of this equation a ratio of squares. And as such, I could simplify this expression by simply taking the square root of both sides of my equation. So as I do so, we'll take the square root of 7.50 on the left side, and then on the right side, we've got the square root of 0.50 plus x squared over 0.50 minus x squared. And I can simplify this now. The square root of 7.50 is 2.74. And then on the right side, the square root of something squared is the original thing you started with. So therefore, I would have simply 0.50 plus x in my numerator and 0.50 minus x in my denominator. And this all of a sudden looks like a much friendlier expression to solve algebraically. I'm going to go ahead and multiply both sides of the equation by 0.50 minus x to get it out of the denominator, yielding the expression 2.74 times 0.50 minus x is equal to 0.50 plus x. And I'm going to gather my variables and my numbers onto either side. So I'm going to go ahead and subtract 0.50 from both sides of my equation and add 2.74 to both sides of the equation, yielding now a new expression which is 0.87 is equal to 3.74x, and then divided by 3.74 on both sides yields an x value here of 0.23 molar. All right, so I've got an x value here, and I don't need to go about checking any assumptions here because I didn't actually make any assumptions at all. So, easy peasy, I can just now go ahead and determine equilibrium concentrations of all species. For both reactants, the concentration at equilibrium was defined as 0.50 minus my x value of 0.23 molar, which yields equilibrium concentrations of carbon monoxide and water of 0.27 molar for each of those. And then for the products carbon dioxide and hydrogen, their equilibrium concentrations were 0.50 plus x moles per liter. And again, if x is 0.23, that yields equilibrium concentrations of 0.73 molar for both of the products respectively. And remember, folks, you are always welcome to go back and check your work here. If I take those equilibrium concentrations I have now calculated and plug them into my expression for Kc, you'll notice here I get 0.73 squared over 0.27 squared, which plus or minus a little bit of rounding error comes out very, very close to the value of Kc expected there of 7.50 at our reaction temperature. So it seems like things worked out well. All right, so there's another means of some clever math here we can use to solve an ice table. Let's look on our final slide at one final example. All right, for our final example here, we're going to be looking at another ice table problem. But again, remember, an ice table is simply an organizational tool. And sometimes when you're faced with a new and novel way of looking at a problem, sometimes knowing how to use the tool in a new and different fashion is a useful skill to have. So let's take a look here at an example problem, which is example 5, in which we're going to react nitrogen gas with hydrogen gas to form ammonia. And we're given information here that at 200 degrees Celsius in a closed container, we're going to combine together 1 atmosphere for the partial pressure of nitrogen gas and 2 atmospheres of hydrogen gas. And we're going to determine here that at equilibrium, the total pressure in our system is 2 atmospheres. I'm going to ask you to calculate the partial pressure of hydrogen gas in the system at equilibrium. So, with a starting point here, recognizing that this is a good place to employ an ice table, let's go ahead and start by balancing the chemical equation described by our chemical process. Starting off here, we had nitrogen gas, which is diatomic N2. And we're combining that together with hydrogen gas, which is also diatomic H2. And we're forming here in an equilibrium state a product which is ammonia NH3. Now again, we need to balance this equation here, and I'm going to recognize right off the bat that I have an odds and evens problem with my hydrogens. So to fix that, I'm going to go ahead and double the odd number in our system, which means I'm going to take 2 of the ammonia molecules on the product side now, yielding 6 total hydrogen atoms. And as I do so, that also now will be balanced by adding a 3 as a coefficient to the hydrogen on the reactant side. And at this point, we now have everything balanced in our system. Now, importantly here, folks, recognize that in this ice table, up until this point, we've been dealing with concentrations, but because concentration of a gas is proportional to the partial pressure of that gas, we can go ahead and instead describe within our ice table here the partial pressures of each of these species present. So we'll have on our first row there the partial pressure of nitrogen, the partial pressure of hydrogen, and the partial pressure of NH3. And then again, we'll have our I, C, and E along the first column there for our initial partial pressures, the changes now in partial pressure, and the equilibrium partial pressures of those species. And we can now start to fill in the given information into our ice table. Starting off under initial conditions, I'm going to label the partial pressure of nitrogen as 1.00 atmosphere, and of hydrogen of 2.00 atmosphere. And again, because I've been told nothing about any other reactant species or initial species present, I'll go ahead and label a 0 for the initial partial pressure of the product ammonia. And just like we've seen before, given this initial set of conditions, with a Q value of 0, this system must experience a shift in equilibrium to the right, and therefore my changes in the partial pressures of these gases would be, for nitrogen, minus X atmospheres, for hydrogen, minus 3X atmospheres, and for the ammonia, plus 2X atmospheres, again recognizing that those coefficients from the balanced equation are going to inform our relative changes in pressures of these species. And this leaves me now with equilibrium pressures of 1.00 minus X for the nitrogen, 2.00 minus 3X for the hydrogen, and 2X for our ammonia. All right, now we find ourselves now with an ice table that has been completed. Now, that being said, this looks like we now need to change how we are approaching the problem because I have not got the information necessary to solve this with a K expression the way I have been doing up until this point. And the reason why is I don't know the value of K in this system. So let's instead make use of the other piece of information which has been provided to us here. We know at equilibrium, the total pressure of the system is 2.00 atmospheres. That total pressure in the system results from the sum of all the collisions between all particles involved in the system. That is to say, some of that pressure is made up due to the fact that the nitrogen molecules are colliding with one another and the walls of their container. Some of that pressure results from the collisions involving the hydrogen, and some of that total pressure involves the collisions involving the ammonia. So therefore, I could say that the total pressure in our system is essentially the sum of the partial pressures of the individual gases which are present in the system overall. That is, the total pressure is equal to the partial pressure of nitrogen plus the partial pressure of hydrogen plus the partial pressure of our ammonia, NH3. This is essentially Dalton's law of partial pressures, which we have hopefully seen at this point from your gas laws unit. And now that I've defined using Dalton's law of partial pressures the total pressure of our system, I can now go ahead and plug in the partial pressures of each individual gas at the equilibrium state into that expression to solve for our given value of X. So again, the total pressure of 2 atmospheres is equal to nitrogen's partial pressure of 1 minus X atmospheres, plus the partial pressure of hydrogen, which again was 2 minus 3X atmospheres at equilibrium, plus the partial pressure at equilibrium of the ammonia, which was 2X. And I'm now going to go ahead and gather my variables together here. So I've got 2 atmospheres is equal to, let's see, 1 plus 2 gets me 3 on the right-hand side there. And then minus X minus 3X plus 2X, combining all those together, yields an overall of minus 2X. So I get the expression now, 2 is equal to 3 minus 2X. And I'm going to go ahead now and just simply subtract 3 from both sides, yielding minus 1 is equal to minus 2X. Or the X value here is equal to 0.50 atmospheres. All right, so we've got an X value. Now finding those equilibrium pressures of each gas is very, very straightforward. The partial pressure of nitrogen would be 1 minus X. And again, if X is 0.50, that leaves me with 0.50 atmospheres for the partial pressure of nitrogen. For hydrogen, its partial pressure at equilibrium was 2 minus 3X. So 2 minus 3 times the X value of 0.50 yields also a partial pressure of 0.50 atmospheres for the hydrogen. And then ammonia's partial pressure here would be 0 plus 2X. So 2X would be 2 times 0.50, which is 1.00 atmospheres. And you can see here that this now satisfies the criteria that we knew to be true. That is, the sum of the partial pressure of each gas in the system equals the total pressure of the system overall. So the 0.50 plus the 0.50 plus 1 atmosphere equals the total pressure of the system we expected to see of 2.00 atmospheres. All right, so partial pressure of hydrogen gas, therefore, from our calculations to answer the question is 0.50 atmospheres. All right, so kind of a unique way that we can use an ice table not just to solve equilibrium calculations involving K expressions, but also to employ some gas behaviors in terms of Dalton's law of partial pressures as well. So there you have it. There are a bunch of different ways to employ an ice table effectively. Please make sure you just use this as you would any tool. You're welcome to use it creatively and in novel new ways on the AP test. It's really nothing more than an organizational tool that helps you make these calculations for systems in equilibrium. Thanks for listening, and we will see you on the next lecture.